recording. Okay, so let's talk about today's objective. Let me share my screen. Okay, so we'll get into unsupervised learning today, but before that, I wanted to finish up some parts of lecture 5. So last time we were looking at recurrent neural networks, the basics, the unfolding, especially so that it's clear that it's actually a single computation graph happening. It's just a sequence as an input, and typically the most general form, a sequence as an output. And we looked at vanilla RNN, which had a single neural network layer inside with the tan activation function. And then we looked at LSTM. We briefly mentioned about GRU. And then we also started talking about a few example sequence-to-sequence applications, and we'll get back to that, these applications. And I'll also briefly mention the attention mechanism today, for today, and then we'll go to the goals of lecture 6. So for today, the objective is to recap a couple of examples of the sequence-to-sequence applications and then the models themselves. Look at the attention mechanism, and then we'll move on to unsupervised learning. And in unsupervised learning, what's the goal? The goal is, so we have already seen several unsupervised learning problems as well as models before, clustering being a very classical and a popular problem in unsupervised learning. And we've also seen LDA, latent digital allocation, earlier in, I think, 2 lectures ago, where we were doing topic modeling. So those are examples of unsupervised learning, but we'll see a couple of relatively newer, I guess, models for building what I call generative models in unsupervised learning. The 2 models are generative adversarial networks, which is based on, a slightly interesting loss function. And the second one is called variational autoencoder. And that also is related to something called an autoencoder. And we'll look at what is an autoencoder and what is a variational autoencoder. And these 2 methods, GANs and VAEs, help us generate new samples. Okay. And that's basically the objective of this session. So let's actually okay. So last time we were, so let's actually quickly recap the application. So let's start with, so let's assume, for now, we don't really need the internals of a RNN anymore, although that was the subject of, the core subject of last lecture. Let's think of the RNN block as block A. Then here is just to, as a warm up, here is an example for sentence classification, right? You could use, so if you have a sequence of words, let's say you have word to vec from the 2 lectures ago, then you can convert each word to its vector representation. So you have now a variable length sequence of vectors, right? So if a sentence has 10 words, then you'll have 10 vectors. If a sentence has 15 words, you'll have 15 vectors in sequence. And then you pass each vector one at a time. And of course, you'll have an intermediate output. You can choose to ignore it. So you pass on, let's say, H1, and the next vector to the RNN block, you'll get H2 and so on, all the way to the final hidden vector. That, the hidden vector's dimension could be, let's say, D. And then you can just think of, again, converting it into a p-dimensional output if you're doing a p-class classification. For example, if you're just doing positive versus negative sentiment, the p is going to be 2. Okay, and while training, you have the usual. If let's say you're doing 2-class classification, then this is just going to be binary cross entropy or loss, and then you have to backcrop and just update. For example, if it's a simple vanilla RNN, then this will be the parameters of the neural network. So W and B, and yeah, that's it. So all these A's will have the same parameters. So these are the parameters that you update. Okay. So of course, you can see that the loss touches the parameters, the gradient. So the parameters enter here, here, all the way here. So there's some sort of an accumulation of gradients that you need to do. Okay. And in this description, I just mentioned for a single example. So the whole narrative changes once you have batches, because if you have a batch of sentences, they all may not be of the same size. And so then you get in the issue of finding the right batch sizes. So for example, if you have a bunch of sentences, okay, you sort the sentences according to their length, let's say. Then, let's say the top few sentences may have the same size. The sentences in the middle may have the same size roughly. And the bottommost sentences, which are the longest, may have some size. Okay. Now, within at the top, let's say they are roughly on the same size, but of course, one sentence could be of 5 words, the next sentence could be of, has 7 words, and so on. Then what do you do with the two addition? Like, if you want to create a batch of these, so that you do batch, you exploit the batch training, that is, that's a big computational speed that you can do using GPUs. Then you could do paddings. Okay, so you could pad sentences so that they are of the same size. Okay, and there's also pros and cons about why you can add padding and how does it influence the results. Very similar to how we added padding while working with um, conv layers. Okay, so that's sentence classification. Let's jump to uh, image captioning, which again, this is a recap from last time. So if we have already trained so in image captioning, again, think of using a CNN as a feature extractor. It's producing a image embedding basically of the image. And then that is a starting point, which is input to an RNN. In RNN, and then the RNN, hopefully, if it's already learned, then it's going to produce a caption for that image if the weights of it are already properly set. While training, you have to pass the actual, so you will have training data which would include the image and the image caption, which would be some variable length. For example, here it's of length 2, straw hat. Then you have to pass the image input and the straw hat words are their embeddings, are their vector representations, and try to minimize the loss that it does produce straw hat at the output. Okay. So that's image captioning, and the next few slides we're just going over. Okay, if you have an image, if you use VGG16, then at some point you can take a representation of the image, and then you can add it as an extra input while in when you look at like this is the first step in the RNN where you start with the start token. It could have its own representation. And then you do the internal inside the RNN. There is something computed, hidden vector that can be passed on to the next computation step. But you can generate output. Hopefully that output is the same dimension as your, for example, word embedding, and maybe it reflects. You can map it back to a word. Okay. And in test time, of course, if you have an embedding, you can either, so this output is actually, since we have to produce a caption, the output at every time step is actually a distribution over words. So if your vocabulary size is 50,000 dimensions, then your why not is actually supposed to be in 50 dimensions, 50,000 dimensions, sorry. So each coordinate in why not is going to be the probability that the first word in the caption is something like straw, for example, right? So either you can take the word with the highest probability and feed it as the next input, right? Because that's needed to generate the next word in the caption. Or you can take a sample from that probability mass distribution. It's a distribution over 50,000 symbols, right? Now you can get a sample, and that sample would be the input to the next next word generation. Okay, so that's how you do it, and hopefully at some point you're going to get a vector, a probability distribution over your vocabulary where most mass is on the n token. If not, you terminate at some point as well. So if you sample the n token, you stop. Okay, that's when your caption finishes for a test example. So any questions at this point? This is just a recap from last time.
Is there any benefit over sending a word distribution as a next input over a single word?
Oh, we're not. Okay, we're not sending the whole distribution. So why not is a distribution over all the words in your vocabulary from which you can take the word with the highest probability, or you sample from the distribution. Still, you get one word at the end of the day, and you just pass on the next word. So the next word is just going to be one of the words. Okay, or here
Okay,
I
so,
will say.
so you like randomly sample one word from.
From why not? So the hope is that, see, when we trained, for example, let's say this test image is actually a training example, which is, let's say we know its true caption is straw hat. Hopefully, once we've trained, why not is a distribution of words where the coordinate corresponding to straw has the highest probability. Okay.
Okay.
Ideally, the probability is 1. Okay, so whether you sample from it or take the max, it should give you the straw as the
Okay.
input, and so that you can use for the next word generation. But that's for training examples. Okay, and so that's the idea for test examples as well.
Okay.
You either sample or take a max,
Okay.
and we'll talk about it a little bit more again for uh, I guess auto reply or in general machine translation in a couple of minutes.
Okay. Cool. Thanks.
Um, any other question? So auto reply or basically machine translation, going from, let's say, an English sentence to a sentence in Chinese or Spanish or other languages, you have to map. You basically have to build a model which maps variable length inputs to variable length outputs, right? So we saw that this exam, that's actually the generalized version of sequence to sequence modeling, right? So what is auto reply? Just to recap quickly, auto reply is a feature where your app basically figures out from your email what to respond appropriately, and you can typically sometimes it works, and this has also been rolled out in many email clients. So let's see how you would how the model itself will look like. So here's a version. This is the first version where you would have an RNN. So the blocks, the white blocks here, uh, are the RNN individual computation. So you're sending hi, how are you, and then each of these is a hidden output. And at some point, you have the end token where the message finishes. You have the final RNN output, the hidden output, and then you can use that as a um, you can use that as an input to produce the word that you're looking for as the translation or the reply. Okay, so at training time you would have this unrolling. So this RNN, this part is the same as the sentence classification example. So you would have a variable length input. All that information is condensed into the final hidden output of the RNN. Now there's going to be a second RNN, which is going to be taking that hidden output produced by the first RNN as the input, and now it has to produce a word, using the current, this HN, and then keep producing, subsequent. Sorry, this is not going to be shown, but keep producing additional hidden vectors whose transformations would be giving you again words. Okay, and this is supposed to be the response to the input um, string, in this case input email, for example. Okay, so there is two RNN operations. So the second part is essentially a decoder, and the first part is called an encoder. Okay. um, So first version is actually a little bit handicapped. That's why I'm calling it a first version. Here, all the information about your email is in HN eventually, right, after encoding. And from HN, you're just trying to say, oh, what could be the first word, and a little bit of transformation. What's the second word? What's the third word? And so on. Okay. A little bit of improvement over that is that you actually do what we did earlier, where for image captioning, you pass the IM to the as an input next time. And this is actually the typical RNN representation, right? So here there will be intermediate outputs. You don't care about these outputs. Okay. So this is the usual RNN, right? But at the end of the sentence, you care about the output. when you pass this n token, you care about the output. And then from that point onwards, you care about, you pass the output as an input, again, sampling or max. And while testing, but of course, while training, you have the actual output that you care about. So that should be the input here. And you're trying to produce this output string. Okay. Is the encoder decoder representation clear? It's just two RNNs, one after the other. Encoder just is corresponding to the input string, okay, whether it's email or the sentence itself or a paragraph. And the decoder is just gonna use, so encoder, you had ready-made input available. For decoder, you have to somehow, at test time at least, you have to go from previously decoded output to to partially feed for the next output that you're going to create. Okay, so that's the and of course, while training, you feed back the true output that you care about. So even if you predict not IM, so you predict a distribution over words where IM is not the highest probability, that doesn't matter. You still feed in IM as the input here. Okay, so that's training, because you know the true output sequence that corresponds to the Y pair in your training XY pair. Okay. I want to introduce again this question about sampling versus taking the max. That's good, but there's something more that you can do. So, for example, for that given input sequence, let's bundle all the vectors together, the whole sentence. We generate a first output. Okay, why not? Okay, let's say we are going with the max probability approach. Okay, so we get this distribution over words, and then we take the word with the highest probability. Then let's say, and now we have the partial output, right? So we chose the first word to be the word with the highest probability. Then we feed it again as input, right? Like I am here. And then we produce another word, which also has the highest probability, and so on. Okay. So picking the word with the highest probability in this manner, stage by stage or step by step, is essentially a greedy, I guess, strategy or a greedy algorithm. And there could be mistakes. For example, if there is a mistake made in the first word itself, like the first word is not I am, but you are. Okay, hi, how are you? And then the first word happens to be with high probability you are. Okay, then you are is going to be fed to the next, instead of I am here, you are. Sorry. Okay, or with the apostrophe. So if you make a mistake early on, you would be constrained to kind of propagate that mistake through the next few steps of your RNN when you're generating the output. So one idea from audio signal processing days, or an old idea in that literature, is the idea of beam search decoding. Okay, it just tries to guard against making errors early on, which may propagate later. So, for example, this way of decoding, or this way of figuring out the response sentence, if you're doing auto reply, is the following. You just maintain a list of k best candidate output sequences at any given point of time, okay, till you see end. For example, we have x as input, so we don't just so x as the input email. Then we don't just take the maximum, like when we first output why not here, um, here. We don't just produce, we just don't take the maximum, but also take the second best and the third best. For example, let's say we take the three best answers, three best words. These are the words with the highest probabilities. Okay. Next, we'll use each of these words and uh, go down into three scenarios. Okay, what if the first word happens to be high? What would be the second word? These are the three second words. If the what if the first word happens to be yes? Then these are the three words. And what if it's please? Then these are three words. Okay. So you maintain. So you can see that every time there's a combinatorial explosion here. So for every word, it produces three additional words. Like three children, and those three children, if again I choose three, there's going to be three more children, and so on. Right. So there's going to be combinatorial explosion. To restrict that, you just keep you prune to keep only those paths, right? Or only those paths in this tree which are the most likely, which are only up to k top likely paths. Okay. So how am I getting the top likely paths? You just multiply the probability times the probability times the probability. Okay. Because each word comes with the probability that it was the probability that word was the output, right? So that's beam search decoding, and so that's just a trick that I wanted to point out. Now let's actually uh, talk about attention as a solution to a problem. And the problem is as follows. The problem is that the link between the encoder and the decoder is just this one node. Okay, so let's say the email has like 3 paragraphs, or the email has one sentence, 10 words. All that information has to be so all that information has to be okay. There was a question. Condensed into HN. So the question is it possible to pass a variable length sentence rather than passing a word? Variable length sentence. So we are always talking about variable length sentences, right? Okay, you're saying the question is about whether we pass on X, we pass instead of a word a sentence itself. Yeah, as long as we have, like, if you have 10 sentences in the email, if you had a sentence to vector representation. So there's actually sentence to vec, for example, similar to word to vec, there's sentence to vec, document to vec, all sorts of vector representations of objects which are not purely, a vectorial or a numerical object, right? So you could have a sentence followed by a sentence followed by a sentence. If you have 3 sentences in an email, then each sentence somehow should have a representation. If you have that representation, then you can pass sentences as well. Is the weight matrix invariant? So yeah, here, yeah, just think of RNN, right? So RNN had the same parameters, right? First guy, second guy, third guy, fourth guy, all have the same weights. So similarly here, the weights you can keep them fixed. Yeah. Because so here's the thing, right? So we are matching variable sentences, variable length inputs to variable length outputs. So it's not like we will train. So if you only trained, up to 5 output separate weight matrices like these weight matrices, and if you were expecting a 6 or 7 length output, then there's going to be an issue. But anyway, that's not the reason. The reason is you do retrain the same weights across all the steps in this forward pass. You can change it and see if you get something different, but I think that's a design choice you can explore if you want. Um, yeah. So I was just talking about the need for something better from this, right? So here I was just trying to point out that no matter what the length of the output is, length of the input is, whether the email has 3 paragraphs or just 10 words, ultimately all that email information somehow has to be condensed into one, this final hidden vector hn, and from there you're now expanding out what is the whole realm of outputs that can be generated, right? A good output, and so this vector is actually fixed length, right? Maybe 100 dimensions, maybe 50 dimensions, something. So it's unclear whether this fixed length vector is going to capture all the information that was there in the email. Okay, um, so so one way to fix this is to use what is called an attention layer. And the simple idea is that instead of just basing off your decisions of generating these words, like output words, based on just this hidden layer, and of course, like for example, thanks is based on this, based on the current word and the input, right? But what if I base any word? So let's say I am not just on the current input and the 2 inputs to the RNN block here, but also all the previous hidden outputs. Okay, hidden outputs when during encoding time. Okay, so that's the key idea. The idea is simple. All you're saying is when we're generating any word at the output, let's say I am or thanks or even end, whenever we want to generate this let's say 4th word or 5th word at the output, we don't just decide on the 2 regular inputs at the beginning, like the previous word that was generated as well as the hidden output from the previous step, but also somehow go back and see if there was a representation that was useful. Okay, go back and see if any of these hidden vectors were useful to produce this current word. Okay, and let me concretize this with an example. So I just added some slides in this note. I think it's also shared, but I'm not sure if it's linked on the page. Somebody can check and let me know. So let's talk about, so what is attention doing? Um, so this example is actually for not for auto reply, but for machine translation. So so what are we going to do? So let's say we have encoded. So we went through an RNN. So we produced these hidden vectors. Okay, so these are so this dot here, these 4 dots represent the hidden vector that I produced when I pass the word ill. Okay, and when we pass these word, this word, this word, and this word. Okay, so these are the 4 hidden vectors, or basically these squares represent the RNN block. Now, what are we going to do? So now at this point, we want to start generating the output. So because we gave a start token here, so this is up to this is encoding part, right? And this is we are decoding. So while decoding, we're gonna create some intermediate numbers first. So first, let's so now so I'm only going to describe not training. Okay, here I'm going to describe how attention is going to help us. So here all the parameters are already trained. Okay, I'm just going to describe how an attention mechanism works, not through training, but once let's say we already had attention, how would it work? Okay, so we have the start token. So that is taken as an input. And then what we're going to do is use the start tokens, um, uh, the start token and the final, encoder output, those to produce a hidden output, right? Um, um, yeah, so hidden output, that's, let's call it S1. And that hidden output S1, we're going to somehow use it with every hidden output that we produce. So there are 4 hidden outputs that we produced while encoding. Right, so let's use S1 and S1 and currently let's say H1. So this is H1 here. This is H2, H3, and H4. Okay, those are the hidden outputs that I produced during encoding. Okay, if it's a longer sentence, I'll have a longer number of such guys. So using the encoder hidden state and the decoder hidden state, so this is fixed for now. As in this, since we are trying to produce the first word, S1 is fixed. Now we use S1 with H1, produce a number. Okay, so I'm going to talk about how we produce that number. But given H1 and S1, those are inputs. Those are fixed at this moment. Given those two, I produce a number A11. Okay. Similarly, I'm going to use again S1 and H2 to produce another number A12. Okay, similarly, I can produce A13 and I can produce A14. Okay, now these numbers, what I want to do is to somehow use these numbers as an indication, or transformation of these numbers as an indication of which hidden, I guess, which part of the input is responsible for my current output. Okay, so that's the goal here. The goal is that the information that I'm passing from the encoder in the previous versions of our solution, the encoder was all constrained to somehow produce a single fixed dimensional vector, whatever be the length of my input, if it's a long sentence or a short sentence, and then use only that information to start producing output. So, right. But instead of that, what we're trying to do is try to, again, go back and see what were the hidden outputs and try to use them to figure out the current output. Okay, so let's come back to our story. So we have just S1. We used S1 and every hidden output currently to produce 4 numbers in this example. Now we're going to renormalize those 4 numbers. So let the 4 numbers be called A1. Okay, so we're going to use just a simple softmax operation to convert them into numbers between 0 and 1. In fact, we're going to make it a probability distribution. Okay, and this you should know. Once we have scores, we can always, and the scores can be, each of the score coordinate could be positive, negative, whatever. But the moment you apply a softmax operation, we get a representation called alpha 1. Which is essentially a vector, right? It's a probability vector because the numbers are going to be between 0 and 1, and they sum up to 1. Okay, so now we just apply a softmax operation once we have these attention scores. Okay, they are called attention scores. So once we have this, transformed, basically squished numbers, then we can use those squished numbers and the hidden values again. Okay, so we already use hidden values to get to these alpha 1 1, alpha 1 2, and so on. Okay, from a11, sorry, yeah, a11, a12, and so on. Once you have these probabilities, we're just going to take an average. Okay, average of what? So we're going to take alpha 1 1 times h1 plus alpha 1 2 times h2 plus alpha 1 3 times h3. So first index is just for because we're producing the first output. Okay, plus alpha 1 4 h4. We're just going to take an average of the hidden vectors. Okay, so now you can see that if the alpha scores were such that the first coordinate has the highest probability, then in this average h1 will have a higher, I guess, influence than h2, h3, h1. Okay, so what we're going to do is use this, and so what we're going to do is use that average number and the output of my decoder's RNN. So the decoder RNN would have some output. Let's call it. Oh, sorry, it's the same output. Sorry, the S that we were using. So S that we were using earlier to produce these codes. So, sorry, this S1. So we'll use S1 and this averaged number. Let's call it Z1. We're going to use these two and concatenate them. So Z1 and S1, concatenate them, and then just do a linear transformation. I guess not linear, but some transformation G. And once you do the transformation here, we're just showing that you can do a softmax operation as well. So ultimately, you want to get a y hat 1, and this is, as I said, if you're doing auto reply or this language translation, it has to be the size of vocabulary, right? Vocab size. And of course, hopefully that coordinate is the highest, which is actually the right translation at that point. Okay, now yeah, and let's say we produce something let's say in this case word he, then we're going to pass it back to for the second input. He is the second input and the previous hidden the decoder's hidden output. Now we're going to produce S2. Now again, S2 is going to interact with the same H1, H2, H3, H4 using that function f. I haven't specified the function, but using that function f to produce now again attention scores A21, A22, A23, A24. I'll squish them again. I'll get these essentially a probability distribution. And again, I'm going to average these hidden vectors. And you can see that because this guy has a higher probability value, or a number between 0 and 1, which has higher weight on the last hidden vector, this vector will be closer to closer to this vector, right? And then you can use this and S2 again concatenate. You don't have to concatenate, but in this example we're concatenating. So S2, so Z2 and S2. We're going to use it together to produce y hat 2, which is our prediction for the next word. Okay. So what's changed is previously we were producing S2 and we were not doing attention. Directly from S2 we were trying to produce y hat 2. Okay, so the same link here, but this link was not there, right? Now we have additional input to help us better position which word it should be. For example, maybe the second word should rely on the last word seen at the input. Okay, the last word seen at the input is here, and maybe it has a significant influence, should have a significant influence in this language pair to produce the second word. Okay, for example, you know that some sentence constructions in different languages, the order of nouns, verbs, are kind of reversed. So that's what this example is trying to show. For example, maybe for the first word, you do want to refer back to what the first word was in the input. Okay, so that's the notion of attention. So while generating the first word, you're focusing on the hidden output produced by the first word, and for example, for producing the second word, you happen to focus on the last word. Okay, so now this focusing of attention, or basically focusing on one of the hidden outputs of the encoder, that's all data driven, because these weights, so this probability being high is just dependent on this hidden output and the h4 itself, right? So these weights are all data driven. So that's what makes it quite a versatile tool. And it's observed that this actually gives a good boost, a decent boost to many of the sequence to sequence models that we've been talking about. So similarly, you can repeat same thing. So S3, previously it used to be S3 directly to produce with let's say a simple feed forward network to produce a distribution of vocab. Instead of that, now you concatenate Z3, which is the average of weights times these hidden vectors. Okay, and then do the transformation to produce this third output, and similarly fourth output, and so on. Now, um, yeah, so this is how you sentence you create a sentence. So this attention mechanism is an additional innovation, and it's not just for a sequence task which involves um, pair of sentences to sentences, but there are other sequence tasks. Maybe in a later lecture we can talk about attention in an image localization setting. It's a slightly different problem, and there also you can use this type of an idea. Okay. Um, so let's now talk about the thing that I did not mention. What is that f, right? So there was an f of st or ht comma, sorry, f of ht comma st for every ht that was in the hidden, sorry, that was in the input. So that was on the encoder side, right? So there was a hidden decoder state ht, and then all the capital T length hidden vectors on the encoder side. We were using a transformation, right? F um, to get attention scores. They were getting squished, and then they were ultimately leading to Z, and Z was getting concatenated with the hidden ST, the original ST, and then you're producing the y hat. Now, what is this f, right? So what is this f? That's the only thing to kind of shed light on now. Um, it could be a simple function. For example, it could be just an inner product between, if they happen to be of the same dimension, it's just an inner product between. So this is a design choice. Different people have experimented with different choices of how should the decoder's hidden output interact with encoders hidden output. So this doesn't have parameters. This multiplicative attention function here, it has a parameter w that also has to be now learned. Or you can have much more complex attention mechanism where you transform both the hidden vectors and take a do a nonlinear transformation and multiply with a parameter. Okay, so these are all function choices. The moment you have two inputs, you can have all sorts of functions. So these are some examples here. So any question about this part? Okay, so I think what I explained above is exactly what you can do. So when you're producing okay, so in this example, when you're producing the second word, you focus on which word could help you produce fine as the response, essentially because of your that attention vector. Maybe it's still the distribution would be such that maybe you have to focus on the first word to ensure that the second word is um, fine. So is this a new question? Weight matrix invariant across the network. So, okay, if you're talking about this weight matrix, yeah, I mean, so here is just a choice of the attention function. So that's fixed.
I
So a
think
lot of things are fixed. Yeah. Yeah.
that's the old question.
What is it?
That's the old question.
Oh, that's the
It's
whole question. Okay, so just to say that, I mean, again, same thing here. If when the moment there is no indexing, it means that these functions are fixed. Okay. Um, yeah. Yeah, I think in this next slides, I'm just showing the same thing of how to get attention for the back to the auto reply example. Okay. So if there are no questions about this part, then let's go back to our other slide deck. Auto reply. So this is the same thing. Yeah, I think we are pretty much done. As I said, we may revisit this. You can do visual attention as well. So where you can figure out by trying to localize an object, or here I think you're trying to Um, um, oh yeah, here you're trying to, so here I think this is a number. So you're trying to do object recognition. So you can focus on different regions while trying to produce, your output. Here, I think I did not even describe what the problem is. But in general, you can apply attention to even images. So you can attend, you can look at, you can, it's all data driven. So it turns out that for some out, when you're trying to generate some output, uh, like for example, in the image captioning setting, the straw hat, it could be that while producing the hat word, you can focus on some part of the image. Okay, so you can do something like that, and we'll come back to this attention aspect again um, in one of the later lectures. Um, if there are no questions, then we'll skip. We'll go over to the today's unsupervised learning material.
Can we quickly do how do we generate that A, like in the very first? So
Yeah, that's a good question. So yeah, I think it's useful to understand the core idea here. This A vector, yeah. So let's focus on one of the slides, right? So I have the S1. So let's say we have trained the RNN. Okay, we have the encoder weights, we have the decoder weights. Okay, it's the same weight here, by the way. WB, some weight WB itself, or maybe there are four weights if it's a LSTM, whatever, four pairs of weights. So we've already, so let's say we have now this test input, and we have produced a final embedding or a final H4 that needs to be passed on to the decoder. We've produced that, and we also produced H3, H2, and H1. Okay, we've already produced it. Now to start decoding, we have to produce. We have to this customary to start with a start token, and you input the start token. So you can do the first step of decoding. So to produce the first hidden output S1. Okay. So without attention, you would have just produced from here to some y hat 1, which would be a distribution of your vocabulary, right? So maybe some word should be the first word. Now, what you're doing to produce this A vector, so in particular, for example, A13, is just use S1 and H3. Okay, so H1, H2, H3, H4 have been produced. Therefore, keep them fixed in that order. So every time you produce, let's say in this case, you produced a first decoding hidden output S1, you just use S1 and H3 to produce A13. Okay, so how are you going to do this? This is what I was explaining towards the end. So A13, for example, 1 just represents the first decoding output, 3 represents the third hidden input, sorry, third hidden output on the encoder side, is equal to, for example, could be just as simple as H3 transpose S1. Okay, so these are just numbers that you can compute. Okay, not just A13, you can similarly A11, A12, and A14. Okay, but these are numbers will not be between 0 and 1, so you just apply a softmax operation, and that will give you once you apply the softmax operation, that will give you this bars that you're seeing.
so how does it change for A12? The distribution will change, right?
No, the distribution will change when you're generating the second. So the next lets you go to when you're producing S2. So once we produce the distribution, we want to produce y hat 1. Okay,
Okay.
done with that. Now you forget about the first distribution. Okay, we produce y hat 1. Use that, for example, the max or the sample stuff that we're talking about earlier to produce the word here. Okay, use that word as an input and the previous S1 as an input here. And then you'll get an S2, right? That's the RNN block. And you'll also have something to, let's say, S2 itself to pass it forward to the next step. Now you produce S2. Again, you use S2 and each of these four guys to produce the next distribution.
Okay, so A1 doesn't change, but just some transformation with A1 and S that changes, and that changes the distribution. So that average
So
is
when I say A1, so the indexing 1 represents this attention is only related to the first output. Okay, and when it's done. So you don't have to remember A1 anymore.
okay.
Right. So I have these intermediate outputs, right? So this A's that I computed, like I was just talking about A13, for example, the 1/3 coordinate of A1. This is how you produce it. Okay. Once you produce them, you just do a softmax operation and convert them to a distribution, right? Once you get the distribution, you are just using that and S1 to produce y hat. Okay. Ultimately, all this distribution is to produce a Z1. okay, which is just a weighted average of the hidden H1s, H1 2 3 4 and A1 2 3 4, like this, sorry, A11, A12, A13, A14, produce Z1. Using Z1 and S1, you just go and create Y hat 1. And then you forget about these numbers that you computed now because you don't need them anymore.
Okay.
Okay. And for the next input, you again restart the whole process, as in you already have hidden vectors. You have S2, again produce a distribution similar to this, and get Z2, and then Z2 times Z2 and S2 together, maybe concatenated, will produce Y hat 2.
Okay. Okay. Cool. Yep.
Pre-trained models. There are, yeah, I mean, all of these can be pre-trained. I'm not sure if there are popular pre-trained models with sequence to sequence in these type of LSTM based models. There could be. I'm not sure. Um, yeah, I'm not sure, but I don't see why you don't. Uh, you could have pre-trained models here. There is no fundamental issue preventing you from pre-trained models, except that you will see that the more recent models, which are based on attention mechanism again, but using the transformer architecture, which is a slightly different, architecture. We'll visit that architecture a few lectures later. I think four lectures from now. Then we'll see those models. You will see pre-trained, NLP models available online. Those are more recent. Okay, so so now let's go back to lecture 6. Okay, so we'll start, just at least introduce the unsupervised landscape, and then we're going to take a break. Okay, so today's objective, as I said, the learning goals are to understand unsupervised learning and the context of generative modeling, because these two are generative models. Of course, understand autoencoders and variational autoencoders, as well as GANs, how they are different from each other, and what are the building blocks for each one of them. And so those are the goals for today. And as in terms of outline, today we're going to look at 3 blocks. So first we'll just introduce ourselves, reintroduce and recap, and you'll see some of the methods names that you've seen before. What the unsupervised landscape is. For unstructured data, it's a little bit more difficult to work with unstructured data like images and text. So we'll try to focus a little bit more on that. And then after the break, we're going to cover these 2 methods. Okay. So just to recap, many of you are familiar with this. Supervised learning, you have inputs as well as outputs or labels. So you have basically a training data. Now, a lot of things are pushed under the rug, because to get these labels, you may have to actually spend money, or spend resources to actually tag your inputs. Sometimes they're easy to measure, like for example, you can see the sales tomorrow, or click-through rates and so on. But sometimes, for example, if you want to build a supervised detector of tumors, then some radiologist or somebody has to go and give you the true labels of where the tumor is and whether the tumor exists or not, right? From images. So, but once you have that, you have training data, and then your objective is to just map from feature to the label. Okay, and these maps can get more and more elaborate the moment you have input and output, inputs and outputs being more, I guess, complicated. And you saw that in sequence models, the input and output are actually symbols, and so we looked at RNNs for that. Now with unsupervised learning, we don't have explicit labels, although we can create some implicit labels. So for example, for language models, right? Language models, the next word is the label. For example, language model is essentially trying to predict what's the likelihood of the next word or the next few words given the previous word or the previous few words, right? So there you don't really have to explicitly tag anything, because your next word is your label. Okay. But in general, unsupervised learning, there's not going to be any any labels. For example, images, the medical images that I was talking about. The goal is to learn some patterns of the data. Okay, so you just want to learn patterns of data, maybe you can cluster your data set, your images into, maybe depending on their patterns of different types. Okay. And more importantly, there's no objective measure of success. So that's going to hold even for GANs and VAEs. So GANs and VAEs, as you'll see, are mostly used for image related data sets. And so you have, so maybe GANs and VAEs that we'll see later today, they'll produce some images, okay, because they are generative models, so they can generate new images. You can look at the images to say what the measure of success is, but there's really no objective measure of success. And that was true even for clustering techniques that you saw before. I mean, in some previous class. So let me just list some of the unsupervised learning tasks: clustering, association rules, PCA-based dimensionality reduction, for example, density estimation, for example, just finding the. So here I'm just talking about maximum likelihood estimation, or even using EM for some more difficult to try, tackle estimation problems. Um, EM just stands for expectation maximization technique for estimating parameters of a more, let's say, more complicated density function. What we'll see today, I guess, some of the new things are just embeddings and sampling. Okay, these are uh, tasks where you just want to, for example, you don't have labeled data, you have unlabeled data, and they have, and given new unlabeled data, you can produce an embedding of this unlabeled data point. Or you have unlabeled data from which you created an object, and the object, for example, is a GAN. From that, you can sample a new um, data point. Okay, and for example, a new image, and that image is not just an image in the training data. It's a new image. Okay. Um, so okay, in these slides, I'm just showing. I guess the first picture was clustering. Second one is association rules. Um, and I will not spend much time on it. I think some of you have seen this. For some of you who have not seen it, please, it's a good idea to go and check with these ideas. Dimensional reduction, we have actually seen TSNE, stochastic neighborhood embedding, I think. And then there's also, okay, there are some new nonlinear embeddings that are popular, and I think we referenced this probably when we were talking about debugging CNN. So we had these embedding, these image embeddings, and then we wanted to understand how well the CNN does its classification. So, for example, for CIFAR 10 that you guys did in the assignment, you can project it back to 2 dimensions, the embeddings that you got, and see whether the 10 classes are clustered together with each other in the 2 dimensional space, and also away from each other, so away from other classes, right? So that's dimensionality reduction. Um, And then density estimation, as I said, is just about fitting, for example, typically a parametric model, parametric density function. For example, here, like a mixture of two Gaussians. Here, maybe if trying to fit a Gaussian to this data, um, and examples like this. Okay. Um, no, embedding, as I said, is you learn an embedder, and this is just a quick teaser on an embedder. So we're going to actually talk about it a little bit more. Um, so this is called an autoencoder. Okay, it somehow embeds all your data, let's say images, into vectors without solving a supervised learning problem. So, for example, when we trained ResNet 18, we did not train it. Right? When people trained ResNet 18 or ResNet 50 or VGG 19 or whatever, they were solving classification tasks. But at the end of the day, we can reuse that architecture to produce our image embeddings, right? So image embeddings were a side product of solving a classification task, hopefully really well. Now, instead of solving classification task, you can have some other task such that we still get some embeddings of our images. Okay, and we're gonna get into this particular figure at that point. Okay. And sampling is, as the name suggests, we want to produce new samples. So if you had let's say a Gaussian, you can produce samples from it, from random.random, or from the numpy.random functions, or modules. You can get them. But if you had to sample new images, like how would you do it? and that's actually the running examples today using VAEs and GANs. Okay? So sampling is just producing new images that are from the distribution of images. Okay, so from the distribution of images itself is hard to kind of conceptualize. So what is the distribution of images? But think of a distribution which encompasses all natural images. Then if you get a draw sample, is there an object that from which we can object that can allow us to do that? Okay, do that sampling. So let's spend a little bit more time on learning a distribution. If I've been given a large amount of data, okay, from a distribution PD, okay, we don't need to know it, but let's say we get a draw a lot of independent samples from PD, then we want to estimate PM. Okay, the subscript M just represents to a model, okay, such that the samples from PM are as similar to samples from PD. Okay, let's say PD was itself a normal distribution. Okay, we got the samples, 100 samples from it, and then um, it just so happens we are trying to fit a model which happens to be a mixture of Gaussians. Okay, so sure, if it's a mixture of Gaussians, we'll have parameters mu1, mu2, and sigma 1 and sigma 2, and a mixture proportion pi and 1 minus pi. Okay, once we get that, then we want to figure out if we can get a good, good estimates of these guys. Okay, such that the samples once I have PM, the samples that I draw are as good as very similar to the samples I get from PD. Okay, I mean in this example, if it was a normal and I'm fitting a mixture of normals, clearly you should be able to set one of the components to 0 and should be able to get the same mean and the same variance, for example, right? So there are two approaches to do this, to construct this object PM. One is an explicit construction where where you can actually, okay, I think let's not worry about this. So once you construct an explicit PM, you can do a lot of things. You can draw samples from it. You can calculate expectations. You can calculate all sorts of moments, variance, and so on. And you can also compute averages. So that's what I said, expectations. Or you can also do other things. If it's joint distribution, then you can compute conditionals, marginals, and so on. Now there's another approach to get to PM, where you somehow create an object. Okay, it's like a function. Okay, it's not a so if it's a mixture of Gaussians, you know exactly the expression, right? So it's pi times normal mu1 sigma 1 plus 1 minus pi times normal mu2 sigma 2, right? So you have this expression. So this is explicit, and the other way is to do it an implicit way, where you somehow create a function with, of course, it will have some parameters, such that you will be able to only do this part, which is generate samples. Okay, you will not at least be directly able to do averaging, like directly able to produce expectations. That's okay. Once you get samples, if you get lots of samples, you can do the Monte Carlo way. Once you have lots of samples, you can just take an average of the samples, and that's an estimate of your mean of the distribution, for example. Right? Here's a figure taken from a tutorial from 2016, where they have basically a chart showing how methods are related to each other. So there are a lot of names here. So what to notice is that there's an explicit density description, or implicit this PM description, and in the implicit side there is this method GAN that we're going to look at, and on the explicit side the method is going to be a variational autoencoder. Okay, so those are the two methods we're going to look at: one implicit, one explicit. But we're going to think, since GANs can generate samples, we'll focus on variational autoencoders also generating samples. Okay. Okay. So before we talk about explicit and implicit approaches, just to further disambiguate it a bit, when would we be okay with an implicit approach, where it's basically a function or a black box, right? It's producing samples. So the only thing you can do is produce samples from that black box. Maybe that's not a good picture. Yeah, only thing you can do is produce samples from black box. Whereas in the explicit, you actually have the probability distribution, so you can actually find like some more x. So you can do averages, right? Expectation of x and so on. In the implicit approach, you can produce samples, and from samples you could potentially go to averages and so on. So when would an implicit approach be okay? When you don't need expectations. For example, you just need some future. When you just, for example, want to just get some samples. Okay. For example, you could have a box which is producing all the future trajectories of stock prices. Okay. You don't need to. So once you have these future trajectories, those are future scenarios of stock prices. Then you're probably fine with just that as an output because that was your goal. Okay. Um, because, for example, for each scenario, you can plan, for example, a portfolio allocation strategy. Okay, so the samples themselves are useful for the decision-making task. Or you can, so here is an example of what is called an image super resolution task. So what you actually have is um, what you have is um, an image. Okay, it's a low resolution image, and so what you're going to do is to create a high resolution image from that image. Okay? Image to an image. And so this is an example. This is not an so this is an example where the box from which you're sampling, the sampling is going to be the new high resolution image, but the box also depends on the low resolution. It's a conditional property. Okay, it's not PM, but PM given some input. Sorry. Okay. So the hope is that from low resolution image, you've learned something good, so that you can actually increase the resolution, and hopefully it's comparable to the original here. So this is just an example where you don't need to know the explicit distribution, you just need samples. Similarly, there are many other tasks, and many of these tasks are, as you can see, not unstructured data. So for example, here you're going from segmented image to the image itself, or an aerial map of an aerial map to a road map, for example. So here you could do these things using supervised learning, but you can also do it using boxes, black boxes, which are like samples, okay? From which you can get samples. But these are all advanced, and there's a lot of bells and whistles for each example. So let's focus on two models concretely. One is an explicit generative model called variational autoencoder. By the way, generative just means that from data you are learning essentially an object which represents the distribution of this data, and from which you can sample. That's why it's generative. So explicit VAE and implicit is a GAN. Okay, and these are just examples of ways to generate new samples. For mostly we'll be focusing on unstructured data, which are images. Okay. And of course, why are we studying it today is because both of them will be using neural networks as a core, and you'll see some new objects. For example, the new object for VAEs will be not just because they're images, there'll be some CNN type of, the building blocks of CNN will be present. So con layers will be present. There'll also be a, I would say, let me use the word transposed con layers. Okay, some new layers will be present. Okay, I guess that's one of the reasons why we're also looking at these models, just to expand our list of layers that we know. Any questions at this point? So let me summarize what we're trying to do. Okay, we're going to look at two models, VAEs and GANs. So with either model, at the end of the day, we want to create a sampler. So we want to sample a new image, for example. So the way it will work is that VAEs or GANs will be essentially from VAE or a GAN-based approach. We'll be able to make some block like this. Okay, this is that box I was talking about. So this box in yellow is what we will create, such that if it's given a random input, let's say a sample from a unit Gaussian, okay, because it's a neural network, so things are not running here. It'll have some parameters. We'll talk about the internals of this neural network soon. But both VAs and GANs will produce this yellow box, so that once it's given an input, which is a random vector, Gaussian vector, then it's going to produce dots. It's going to produce it's going to produce samples from this generated distribution. Okay, so this yellow box represents a generated distribution from which you can get samples. Okay, so p hat of x, so you can get samples x's, and then you can think of that as the empirical distribution over x's. And the hope is that there is a true data distribution, for example, on the images, but you only have, among the true data distributions, you only have actually a bunch of images, right? 100 images, 1,000 images, those are those dots. And hopefully using those dots, you can try to learn a good distribution over images. Okay, so those dots are the actual images that you have, those unsupervised data. You want to learn the screen thing, and to learn that, you essentially learn the parameters of the neural network. So we'll get into the details, but I wanted to mention that at the end of the day, what you want is this yellow block, okay, which when given a random input produces hopefully a random output, a sample from the distribution of images. Any questions at this point? Okay, if not, let's take a quick break. Let's assume at 4:59. Okay, so welcome back. So now we're going to look at autoencoders and variation autoencoders. Yeah. So for that, so before we understand, I'm going to talk about the architecture of an autoencoder in a moment. The first thing to notice that we will kind of notice is that a neural network essentially is a transformation, right? It's a function which maps from an input to an output. Okay. So with that in the back of our mind, we can think of the following transformation, which is going from a vector to an image. Okay, at first it may seem, uh, how is it possible? Because an image may have, more number of numbers than the input code, but at the end of the day, it's actually a transformation, right? So it's going from an input to an output, and so it's possible. And to do so, you essentially again think in terms of uh, tensors. So for example, you're going from a 100-dimensional vector to in this example, it's 4 cross 4 cross 1024 dimensional tensor, and then you're going to a 8 cross 8 times the depth is decreasing as you see in this example, to a 512 depth tensor, to a 256 depth tensor, and so on. So to 128 to 3. And as you can see, the height and width are now doubling every at every step. So this is an example of going from a small tensor or a one-dimensional tensor to the tensor that we care about, which is the image. Okay, so this is also a transformation, and let's just call it a decon. Okay, write it decon. So decon operation, although it's not, although that's not the right word here, it should be transposed convolutional network. Okay, although we'll use the acronym, or I guess the short word decon. It's actually this operation of going from a smaller dimensional tensor to a bigger dimensional tensor. It's just called a decon operation. Now, why, how can we do this? To kind of visualize that, you should think of the opposite computation, right? So if we had a tensor like this, okay, 8 cross 8 cross 512, and if you're going from here to here, which is 4 cross 4 cross 1024, right? So we know how to do that, right? For example, we just need to have how many filters? 1024 filters, each one with a depth of 512 and appropriate height and width. For example, if you do 1 0 padding, then you could have a 3x3 sized filter. Then so we know how to go from here to here, right? Now the filter operation is actually essentially a linear operation, right? So if you remember, filter operation was element-wise multiplication. So think of one slice at the output, for example. It was just an element-wise multiplication with the filter's entries, and then add some bias, and that would produce your first number, right? And similarly, slide the filter and produce a second number, and so on. So it's actually just a linear operation. If you vectorize your filter and um, vectorize your input, okay? So that same idea can be used to go from a 4-dimensional vector, for example, to a 16-dimensional vector. Okay. So all I'm saying is, just like in the con case, we were using filters. Okay. So think of the filters correspond to a matrix, and the input tensor, once you vectorize it, is a vector. So vector times a filter matrix is going to produce your output vector, a matrix slice, but you can vectorize it and you can have a vector. So similarly in a decon, this whole decon operation or the transpose con operation at each stage is essentially a matrix multiplication. Okay, it's a linear operation. So and if you look at this. So if you look at, for example, the link at the bottom of that slide, it shows you, that the con operation itself is essentially a matrix multiplication with these matrix weights. Okay, and you can see that the weights are repeated: W00, 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 W00 is all repeated. Okay, so that's how you'd go from a blue, matrix to, let's say, this green matrix. Now the opposite is just the exact transposed, can be essentially the opposite operation, right? So you can do a transpose of this. So this is already transpose. If you drop the transpose, you can go from a 4-dimensional vector to a 16-dimensional vector. Okay. So just to disambiguate that part. So any questions at this point? So all I'm trying to impress on you in the past three, slides is that just like we went from a bigger tensor to a smaller tensor, or it could be a vector, go from vector to a tensor. And the moment we can go from vector to bigger and bigger tensors, we can imagine going from vector all the way to an image. Okay. Logic behind the weight arrangement in the matrix. Yeah. So there's a question about whether there's a logic behind the weight arrangement in the matrix. Yes. So to understand that this logic here, it'll be good to understand the sorry, there is no transpose here. So it'll be good to understand what is the logic for using a filter with the matrix. So remember, so that here, if you look at this picture on the left side, that figure is going to a 4-dimensional vector, right? So A, B, C, and D, and that is the product. That is the output of a matrix, which is 4 cross, that's a 16 because if you see, the input is a 4 cross 4 matrix, right? So I'm vectorizing that. So I have a 16-dimensional vector, let's say x1, I cannot use x's, z1 all the way to z16. Okay, so the filter, so think of no depth here, so depth is 1. So then going from a matrix, so a tensor of this size to a tensor of this size, essentially a matrix operation, a linear operation, where this is the weight matrix. But this weight matrix, it seems as if it has 4 times 16 dimensions, but it's not the case, right? So if you look at the filter, so filter size is actually 9, right? It's a 3 cross 3 sliding filter. So there should be only 9 numbers, whereas it says there's 4 times 16 numbers. So you can imagine that the same 9 numbers appear hopefully at a repeating pattern to get to your 16, to fill up your matrix. Okay, and that's exactly what's going on here. So this matrix here with the transpose is exactly this matrix. If you do the transpose, that's this matrix. If you don't do the transpose, that's this matrix is 16 cross 4. Okay, so if you have this transpose, then you can go from a 4-dimensional vector to a 16-dimensional vector. Okay, and if you rearrange the 16-dimensional vector, you can get a matrix, right? If you put 4 numbers on each row, then you get a matrix. That's how you go from a 2x2 matrix to a 4x4 matrix. So how is this lifting different from kernel trick? Okay, kernel trick is something very different. So a kernel trick doesn't have a linear projection, but it's actually a projection. So projection of going from features to some kernel space, phi of x. It could be finite dimensional, some d2. Let's say this is in d1, or it could be even an infinite dimensional space. Okay, which just means it's a functional space. So and this transformation need not be linear, and you not even talk about the explicit transformation. So you always talk about the kernel, or once you have data, you just think of the kernel matrix, right? So basically, if you did not have any kernel trick, then the data would be, let's say, x, which is n cross d. Then you would just multiply with x transpose d cross n. Okay, x transpose, which is d cross n. This would be, sorry, I think I made a mistake here. Yeah, if this is your data, then ideally, if you, where n represents the number of examples and d represents the dimension, so d1 represents the dimension, then it's as if you're applying every row this phi operation and you get to a higher dimensional space for each example. But here we are only focusing on, like, in a this decon is taking one x and producing an image, right? So this is again a mapping from an input space to an output space. But what we care about for this is actually we want to get an image back. Okay. Whereas here, this is just to ensure that we can do classification better, for example, in SVM. So sure, the similarities are about going from one space to another, typically feature space to some other space. But I think the motivations and motivations end there. There's a question about, okay. So the weight arrangement does have a logic, but the logic can be deciphered by just looking at, what were the filters doing? We did not explain it this way when we're talking about sliding filters. So in fact, the sliding filters are essentially this, right? So there'll be W1, W2, all the way to W9, and then we shifted W1 to W2, all the way to W9, and then W1 all the way to W9. So it'll be like basically a shift, okay, in the matrix. And if you transpose that, you can see that here. So this chunk here is the same as shifted one here, so shifted one here, shifted one here. Okay, so the numbers are small, but let's not focus on it right now too much. I mean, this illustration is too small. But all I'm saying is you can go from any input space to any output space. Okay. Did not be invertible in the sense that the transformations need not be unique. Okay. Clearly, if you want to go from a 4-dimensional space to a 16-dimensional space, if you're going from yeah, there could be many 16-dimensional vectors which all map to the same 4-dimensional vector. I'm saying that there is these things need not be invertible, unique unique mappings between the input points and the output points. Okay, but that's not important here. Let's go to let's now next few slides. I'm going to just motivate. So I just wanted to motivate the decon block, which is going from a vector to an image, so that I can talk about autoencoders. So so let's think about, okay, let me encode a vector which corresponds to an image. Okay, so let's say I fix an image. I wanna have this image as the output. Okay, and I have this whole decon block which has this decon layers. Decon is just an acronym for transform convolution layers, and I have choices, right? Here in the decon layer, I can, when these transformations happen, there are parameters, right? Some parameters, thetas, let's say. So I can choose some input, let's say a vector of ones, and say, oh, this vector of ones should map to this target image. Okay. For that, in order to do so, what should be these thetas? Okay. So you're trying to minimize thetas, or sorry, not minimize, not minimize. I would say set thetas such that this vector of ones maps to a target image. Right? We can do that because this is fixed. And we want a target image. So when we fix vector of ones, when thetas are not good enough, you'll get an image which is not of a cat, right? I mean, or maybe blurry cat, or it could be some arbitrary, image. Now we keep tuning theta such that the between the actual image that we want, which is a cat, and the thing that we're getting when we forward pass from this vector of ones through this decon layers is actually matching with the cat. Okay, we can do that. And we can do that with not just one input. We could do it with multiple input vectors. Okay, so maybe vector of ones represents cat. Maybe vector of half of the ones, half the coordinates being ones and half the coordinates being zeros represents a different target image. Okay, and then we can again, you know, have both vectors represent the target images, so that we can minimize the parameters of the layer such that it ensures that the first vector represents the cat and second vector does actually map to, for example, the dog. Okay, so we can do that. But at some point, you will not be able to change thetas too much because, right, if so vector of ones was mapping to a cat image, vector of something else mapped to another image. The moment I keep adding more and more vectors should map to images, the decon layer cannot simultaneously, help us map a vector to all the target images nicely. Okay. Um, so these input vectors are called codes. Okay, and this network is called a decoder. Okay, and so which is exactly what the picture in the previous slide is just this part. Okay, so it's a decoder, and the codes are also called latent vectors or variables and so on. Okay, these are all just loosely used words. Now what we can do is just think of the opposite operation. The opposite operation is actually something that we have been doing many times over the past few lectures, which is going from an image to a vector. Right, that's just a if you use ResNet 18, it already has pre-trained weights. It'll give us some sort of a good vector. But you don't have to think of pre-trained networks here. All I'm saying is you can go from an image to a vector. That is possible. There's going to be a bunch of weights here. And you can also go from a vector to an image. So there's going to be a bunch of weights here. And that is, we spent some time trying to kind of understand this part a little bit. Okay. The moment you have this pipeline of going from an image to a vector and then vector to an image back, okay, that's essentially what constitutes an autoencoder. Okay, so you have lots of images and unlabeled images, and so you're doing an unsupervised learning task. What you're trying to do is find a representation of these images in an unsupervised way. Representation is basically these embeddings of the images in an unsupervised way. Okay, and what's the goal? Just to recap, just to state it in a different way, the goal is to capture information in this I won't even call training data, in this data of images. Okay, and so the latent variable z is similar to an embedding. So just to as an analogy, when we train ResNet 18 or ResNet 50 or one of these BGG19s models, we are solving a supervised learning task. In fact, the ImageNet classification task. And then as a byproduct of it, we call, when we chop off the last softmax layer, the last fully connected layer or the penultimate fully connected layer, we can just call their outputs, the output activations, as embeddings. Okay. Similarly, we're going to call these Z's, which are produced in this architecture, going from an image through a con and then getting deconned. These are also called embeddings. Okay, same spirit. And but these are obtained using a unsupervised learning task. We don't have labels here. Okay, and typically we keep the dimension of z much smaller than the input x. So actually z is going to be, for example, a vector in 100 dimensions or 1,000 dimensions or something. And input is going to be the actual images, very similar to like the CIFAR 10 images that you have handled in your assignment. And so this point is about, if you choose a larger dimension for the intermediate z's, for example, if z is the same size as x, okay, if let's say your x is 32 cross 32 cross 3, and your z is also 32 cross 32 cross 3, there is nothing to map, right? You can have an identity mapping. Okay, so this whole thing can be identity function, and then you have an image. The z will also be the same image, and then this also can be identity, and z will also, you'll get back the image. So that's the meaning here, to say that ideally z's dimension should be small. If z's dimension is large, then what people do is a different class of models called denoising autoencoders, where they add noise to the input and they still want to get the same output. Okay, but let's not worry about this bit here. Let's come back to the our autoencoder architecture. So what we have is input data, from which we're going to encode it into a feature space. And then from feature space, we want to reconstruct it back. So from feature space, this is the decoder that we were talking about. It's going to reconstruct back an x hat. Okay. And then the way we're going to train the parameters. So from here to here, there's going to be parameters. Here, there's going to be parameters. Theta1, let's say this is theta1, this is theta2. We can train theta1 and theta2 by minimizing this loss. Okay. This loss is called reconstruction loss. You don't have to choose L2 loss, but here's an example. L2 is just sum of the squares of the entries, the differences in each of the, let's say X's are images, then you just look at coordinate-wise differences in the entries. So this is the architecture. And so we have defined the loss function, we have defined the architecture, which has parameters. And now all we have to do is sum over training data, sum over data. So all the X's in our data set, ensure that when X gets encoded, so let's say encoded, and then gets decoded, right? That's the X hat. This part is basically X hat. Minus X, which is the actual data set anyway, it's the whole square in some sense, or if it is, since these images, 2 norm square. Okay, so that's what you want to minimize over parameters, theta1 and theta2. These are the parameters, and this is the loss function, sum over data set as usual, and this X hat is just happens to be decoder encoder of the input. Okay, any questions at this point? Okay, so let me talk about its uses. Actually, although I'm introducing autoencoders in this way, I did not spend too much time on the encoder and decoder details, but if you carefully choose the encoder and decoder, it actually becomes a PCA problem itself, in the sense that if your, forget about images for a second. If your X's are vectors, these are vectors, this is a vector, okay, and your encoder happens to be a linear transformation, okay, it's just a linear transformation. There's no neural network here, so theta is just some sort of a weight matrix, uh, and the decoder is also a linear transformation going from a vector to a vector. Then that is essentially PCA. Okay, so the weight matrix essentially essentially is reducing dimension from whatever is the dimension to the z. Hopefully z's dimension is smaller. Okay, that's PCA. So all I'm saying is PCA is an example of an autoencoder. So autoencoders are richer than PCAs, PCA problem. Okay. And why is it called an autoencoder? Okay, in general, autoencoders are useful for dimensional reduction. They can also be used as unsupervised learning of embeddings. Okay, like maybe you wanted to learn the embeddings of images, then you can do it this way, because images are already in numerical format as tensors. So and then you can use those embeddings, for example, as a uh, warm starting your, maybe you can use those embeddings directly, for example, in a shallow classifier like an SVM classifier, for example. So in PCA, what is Z? Z is the lower dimensional. So in PCA, for example, if you're reducing it to 3 dimensions, so Z is going to be in 3 dimensions. So okay, in PCA, you're mostly thinking in terms of uh, uh, the principal components and principal directions, right? So, but in general, you can think of PC as also as a transformation. So T, it takes X and produces a smaller dimensional vector Z for every data point, right? So Z is going to be, for example, 3 dimensions and 2 dimensions, and X is your usual data set, which is going to be 100 dimensions. Okay, so this, I'm just thinking of PC as a transformation, the projection operation from 100 dimensions to 3 dimensions. So Z is that 3-dimensional output. So there's going to be one Z for every input data point. Okay, dimensional reduced corresponding data point. Okay, so I mean, so Z is going to be just I think if I recall correctly, it's going to be the principal components. So it's the, I don't know if you recall UD V transpose. So principal components are just going to be, so Z is going to be just one coordinate. So this is X, okay? This is N cross D. So if you take an SVD, for example, then Z is just going to be one, what is this, one row vector. Once you truncate the right singular, sorry, the right singular vectors, you don't take all of them, just take, let's say, 3 of them in the V matrix, then you multiply this UDV transpose, then you get 3 numbers for each data point in X, right? So X is N cross D. So the first coordinate would be a d-dimensional vector, and corresponds to a 3-dimensional vector. Okay, that's the. So let's actually come back here. So what's variational autoencoder? Okay, so what we did is autoencoding as a way to get embeddings. But what we want is to generate new samples, okay, new images. And how do we do that? Is to add some probabilistic notions to this process of autoencoding. So what we want to do is to make z random. So imagine if you could make z random, a random variable, then so then z is going to be the source random variable, and there's going to be some transformation, that is decon operation, and then we're going to produce an image. Okay, and so every time I randomly choose z, for example, it's in particular in VAEs, we're going to choose the distribution over z to be Gaussian. Then we draw a sample from Gaussian, pass it through the decon part, which is the decoder part. Then you should be able to get a new image. Okay, and that image should be from the distribution of images, which is kind of hard to imagine, but that's the goal here. Okay, and once we can do that, then we can keep sampling from Z, and we can generate new images. That's the ideal goal. Okay, and so two things need to be changed. One is the architecture itself. First of all, the currently architecture has no randomness. So there's every input training example, like think of PCA, right? There's no randomness, right? So every training example, you convert it into a Z vector, and then you go back to a reconstructed version, X hat, right? So there has to be some change to introduce randomness, and also there's going to be some change in the, so we only have what is called reconstruction loss. So we'll have to change the loss function to introduce some notion of a probabilist, probabilistic uh, loss part as well. And I'm going to describe that. So let's start with the loss actually. So in fact, so in particular, we're going to have two types of two components of losses. So one is called reconstruction loss, which is exactly what we had in the variational autoencoder. Is basically like a 2 norm of x hat minus x. Okay, a square. For example, if x's are vectors or even matrices, you can have a Frobenius norm essentially. The second component is what is going to be related to the probabilistic component of this model. It's called a latent loss. It's going to be a loss on how far from Gaussian is the distribution obtained from the encoder. So recall that we want to make, so we have this VAE, or essentially varying the autoencoder. So but we want here, we're getting z's, right? But we want z's to be from a distribution p of z's. Okay, but we already have a fixed encoder. So for every data, right, x1, maybe x2 and x3, we're already passing through an encoder, and we get some z1, z2, z3. Okay, so we have, for every data point, we have the Z1, Z2, Z3. If you look at their empirical distribution, we want the distribution to be as similar to a Gaussian as possible. Okay, so if it's not Gaussian, we're going to penalize, our model. So there's going to be some parameters to tune, right, for the encoder side. We're going to change. We're going to penalize for that. And so that, how far away is this distribution? This, given this data points, how far away is this distribution at the in the z space is essentially captured by some distance measure similar to like L2 loss function. It's called a KL divergence. It's just measuring distances between distributions. It's not exactly a metric, but it just captures some sort of a dissimilarity between two distributions. Okay, and we're going to use that. So I'm going to talk about, so one more point is that, so the encoder, we're going to, and I think, okay, maybe I'll make this point. This is related to not the loss, but actually the architecture. So I'm going to talk about it in the next slide. Okay. So here's the architecture. So we're going to talk in the next few slides about the architecture, and then bring everything together. Remember, our goal is to generate new images. So to generate new images, there has to be source of randomness. And the source of randomness is that in the Z space, we're gonna start thinking of a distribution being present in the Z space. In the Z space, this means in the embedding space. Okay, so we're gonna change our architecture in this way. Okay, we'll first have the usual input. There's going to be an encoder, and then the encoder is not actually producing a Z itself, but it's going to produce a mean vector and a covariance vector. Okay, or a standard deviation vector. So mean vector is clear. So if you want, as if Z is in 10 dimensions, you can get a Z 10-dimensional vector, okay, which is a mean of this random variable Z. And you're also going to start producing a covariance matrix, but you don't have a matrix, so you can just vectorize it and produce a vector. Okay, so that's going to capture the variance in Z. Okay, and these are deterministic quantities. Given the mean and the variance, I can sample Z from a distribution which has a mean and a variance, right? So those two I'm producing from the encoder. So given an image, I'm producing these two, mu and z, sigma, from which I'm sampling a z, and then I'm passing the z forward. Okay, so that's what I'm doing. And actually, I think I don't show it here. I'm also going to change the output. Okay, so I produce a sample z and I'm passing through the decoder. I get an image, right? So in fact, what I'm going to do is change the output also to produce a mean vector and a covariance vector, or standard deviation vector. And using these two, I'm gonna again sample, and that's sample is gonna be this sample from mean and covariance, and that's gonna be the output image. Okay, so now I introduced. I'm just saying that the encoder and decoders now produce means and variances rather than the embedding itself. Okay.
So that's produced just by using one image, the mean vector.
Yeah, so the way you think about it is, let's say we have the so don't think about training for now. So let's say there's some bunch of parameters already. Let's say it's untrained, it doesn't matter. Some parameter theta 1, theta 2. Okay, all I'm saying is the forward operation, you have to think of it as, given an input, any input image, maybe this cat, you're going to do what for this cat. There's going to be a corresponding mean and covariance vector, the blue part and the yellow thing here for this image, conditional on this image. And then because I have these two parts which describe, for example, the normal distribution is described by its mean and variance, I can draw a sample C. That's going to be the embedding. Okay, it's a random embedding, clearly, right?
Yep.
So for this image, there's going to be some embedding. It's not, so what is fixed is the mean and the covariance. So previously we were just producing directly the embedding. All I'm saying is now I'm going to say for an image, I'm going to first produce the mean and the covariance, or mean and the standard deviation vectors. Okay, that's the only change. So the pipeline is not deterministic anymore. So you're going from an image to a mean and standard deviation vector. From there, I'm going to sample, and then the sample is passed forward to a decon network. Okay, so we're introducing randomness here. But at the end of the day, sure, there's this construction of an encoding and a decoding. But at the end of the day, we don't really care about encoding, right? At the end of the day, I think I described here the goal. What we want is we want to sample from P of Z, and we want to make P of Z Gaussian, and we want to generate new images. And so we only want to go from Z to an image, okay? And Z, we want to sample from a Gaussian. So it's like saying, oh, let me draw a Gaussian sample, pass it through this decoder of the VAE, and I should get a new image. That's like a sample, that's an image from the distribution of images. That's our goal. But to do so, I've introduced this encoder part because that's going to be useful for learning the parameters of this encoder and decoder. Okay, so that once we learn that, we'll drop the encoder part, like this whole thing here, and just focus on drawing something from Z, Z from a Gaussian, and then passing through the decoder. Okay, we'll do that. But it'll become a little bit clearer again as I show this figure again and again, hopefully. Yeah. So there's some parameters. Let's call it theta 1, theta 2. I think I'll change the notation in a couple of slides because there's some specific notation in those slides. But basically what has changed is going from any image. So in my data, I have 100 images. Each of the 100 images will produce a mean and standard deviation vector from which I'm going to sample, and I'm going to try to reconstruct the original image. Okay. So the backdrop has slightly changed, right? So if I, from some number here, right, some number A, I went to a number B. Using B, I somehow created C, right? So B was like a intermediate number. I created C, and then I went to D, right? D is, let's say, the output. So B to C, I'm just saying that it's like B is like the mean and variance of a normal distribution, and from which I got a sample C. Okay. And I want to ensure that A and D are similar. So again, I want to minimize theta, like set theta 1 and theta 2 such that A and D is similar, A and D are similar. So I have to do some reconstruction error minimization, right? But we'll also do, so as I said earlier, there's going to be a reconstruction error as well as a error for, remember going from A to B, we want to ensure that the distribution of, let's say there are several images, all of them will lead to some intermediate vectors, right? Those vectors should correspond to the mean, and that should correspond to a specific Gaussian that we care about. Okay, so P of Z we said is a Gaussian. In fact, we want P of Z to be Gaussian with zero mean and standard covariance. Okay? So that's our preference, and so we also want to change theta, I guess theta 1, so that the z's that we're getting here are close to normal 0 comma I. Okay, so anyway, so let's step back one a bit. The point of introducing this randomness here, sampling Z instead of directly producing an embedding as in the autoencoder way, is so that we can do generalization, as in we can generate new samples, new images. Okay, it's not just a training image. So for example, there may be 100 training images, all of them lead to some, the regular autoencoder, they will all lead to some embeddings. But to generate a new image, what are you going to do? So you need to somehow, get a new embedding, right? New embedding so that you can get to a new image. So that's what we're doing by adding this additional Gaussian distribution aspect into the picture. Um, yeah, so let's so we'll revisit that aspect of what's happening in the pipeline and during training. But you can, so I want to first focus on the results to show that, yeah, results make sense. So samples generated during training are the left and the center, and the original data is on the right side. So this is the original data, right? So these are the samples that were generated after you trained your, after you trained your encoder and decoder. You forget the encoder and just focus on decoder. So on decoder side, you just pick a random Z, propagate it to the decoder, you get an image. Okay, so that could be this image, and so on. Okay, so we are able to, in general, basically create new samples, in the sense that ideally the 6 here should not be the same 6 in any of my training data, ideally. Okay, so that is what is meant by generalization. You can say, oh, if I have training data of images, these images, I can always create new images by just adding noise to it, right? So that's one cheap way to do it, but that's not the idea here. The idea is to really learn the distribution of 6s and 8s and 7s and so on, such that you can draw a new handwritten 6 image, for example.
And what do you mean by don't worry about encoder? So once we have the mean and standard deviation, we
Yeah.
don't. So we
No, our
just
objective is to learn theta 1 and theta 2. It doesn't matter what the mean and standard deviation is. So we're not doing autoencoding anymore, right? So we want to produce new images, as I said. So to produce new images, we only care about this part of the operation, right? So if Z is a Gaussian distribution, then I can sample from a Gaussian distribution, pass it through the decoder, for which I need to know theta 2, and that's it. I get a new image. And that's what's happening here. I learned the decoder parameters, then I sampled a Gaussian, passed through the decoder, and I got this image 6. I sampled a different Z, and passed through the decoder, I got a 1.
so that's for testing, right? So once we are done training, we don't care about encoder part. That's what
Yeah,
you're
yeah. So it's not really testing, right? So we created a generator. This is the
okay.
implicit representation of the data. So we can create new samples from this data, which look like the same as if they're from the same distribution as the original data.
Okay, cool. Yep.
Yeah.
Thank.
So now let's look at so what in the next few slides are going to be probably the uh, most, I guess, notation heavy in this whole, I guess, course. So next, I guess, two slides basically. What I'm trying to do now is to define exactly like what is the loss, right? So we have introduced an object P of Z, and we prefer that distribution of Z is actually P of Z, right? Which is actually, and I also said this is normal with zero mean and identity covariance, right? And we also care about reconstruction, right? And we care about that encoder is such that all the data points map to the Z1s to whatever Z100, if there are 100 data points, the Z should appear as if they are Gaussian, as if they're drawn from Gaussian. Okay, so that's the restriction. So there's a reconstruction restriction. There's a restriction on the embedding space that it has to be Gaussian. Okay, so those two, how do we define the loss function is the focus in the next few slides. Okay. Um, so so if you only focus on the decoder part, so there's some, there's some true prior. So you have to think in terms of priors and um, I guess. Uh, okay, let's think in terms of distributions, right? So p theta star of z, just think of this as a preferred distribution that you have on z. Z is a random variable, and similarly, x is also not now going to be a random variable. Okay, so what the decoder is essentially doing is going from a random variable given z, it's going to a random variable x. Okay, now you can say, oh, decoder is a deterministic thing. Given z, it's going to produce something deterministic. It's not going to produce a random variable. And to fix that, we're going to make decoder, right? So decoder also produce a mean and a covariance. Okay, so that x is a random variable. Okay, so z is a random variable, x is a random variable. And so if there's a random variables, there's going to be distribution over z, and there's going to be distribution over x given z that's captured by the decoder. Okay, and that's, we want to learn this theta star, which is the parameter of the decoder. That's our primary concern. Once we have this, we can always sample from z, pass it through the decoder, you get a new image, right? So let's say p of z is Gaussian. If we're fixing that, so let's say we want z to be Gaussian, and p of x given z is going to be a neural network, which is essentially a decoder, the decon thing that we saw. Okay, and I said and so since it's a neural network, it has to produce a mean and covariance, and it'll become clearer in the next few slides. Okay, and we want to learn theta, right? To learn theta, what we actually have is just data points, right? So x1 to x100, let's say 100 images. So we only have we can only sorry, we can only figure out the likelihood of the data that we have, right? So p of x1 all the way to p of x100. Okay, or just p of x is likelihood of data, generic data point. We want to, and we know that p of x, if I tell you p of z and p of x given z, that actually is essentially gives you the p of joint distribution of x and z, right? So just multiplying those two will give you p of x comma z. Now here you can integrate out z to get p of x, right? So this is just the definition. If you have a joint distribution, you remove one of the variables z, then you get p of x, right? So this p of x comma z is what was written here. It's p of z times p of x given z. Okay, it's just a product. This is just a definition of conditional, and this is a definition of joint. So these two are the same thing. Okay, so that is the same figure. So yeah, so this is our p of x given z. So previously I was just showing z to an x, but x has to be a random variable. And so if x has to be a random variable, I have to first, and we know that we're only, the neural network is deterministic transformation, right? It's just taking a vector, producing a vector. There's no notion of randomness there. So given z, first I transform from z to a mean and a covariance, and use that as a normal, assume that it's a mean and covariance of a normal distribution, and produce x. And therefore now my x is a random variable. Now this makes sense, right? This is parameterized by this decoder network parameters. Okay, that's I think in the previous slide I was using theta or theta star. Now on the encoder side, going from x, we just discussed, we're going to go from x to a mean and covariance of z given x, and then consider z to be a normal distribution given x. Okay, so now z is also a random variable. So and so encoder is represented by q of z. So encoder as in, so there's parameters here, but and z is a random variable. So probability of z given x, let me call it probability, double line just probability, is going to be captured by q, which has parameters phi, which are the parameters of the encoder of z given x. Okay, and similarly probability of x given z is going to be equal to um, p of theta, these are the decoder parameters of x given z. X is a random variable, z is a random variable in this figure. I mean, z is fixed here, so it's and in this figure, z is a random variable given x. Okay, so those are the two parts, and you can see how they're related, right? So this part is gonna produce a z, and that's gonna be fed into the next part. So so I wanted to introduce this because now what have we done so far? So at this point, we have P of Z, which we want to be Gaussian. We have P of X given Z, which is the decoder network parameter. We have Q of phi of Z given X, which is the encoder parameter phi here. And I guess, yeah, this is it. And we also have P of X, which is what we can, we can maximize, this is the likelihood of the data, right? X is the data that we have. So these are all the objects that we've introduced. Okay. Since we have these objects, there's going to be some comparison between objects. For example, sorry, there's going to be some comparison between this guy and P of Z, right? This is a distribution on Z. There's also a distribution on Z, right? So there's going to be some comparison between those two, and we can, in general, there's going to be comparison between distributions. And one measure of comparison between distributions is what is called KL divergence. Okay, um, so KL divergence essentially is it's a formula like this. If you have two distributions P and Q, then it's just the average of P times log P by Q. Okay, for discrete distributions at least, and for continuous distributions, you can have very similar formula. Okay. So it's just a measure. So it's like saying how different is distribution 1 from distribution 2. This is a measure of that. And this particular form is convenient because you'll see next we'll show that maximizing the likelihood of the data. So this is the likelihood of the data is maximizing likelihood of the data is going to be similar, is going to be the same as, because of all these 4 objects that we created, is going to be the same as minimizing the reconstruction loss and minimizing KL divergence term. Okay. So let's look at that. So P theta of X is our likelihood of the data. X is the data that we have, so we can only that's the data, so we can only ascribe a likelihood to it. So P theta of Xi is the likelihood of the data. Let's take the log of it. Okay, we're going to work with log likelihoods. So we want to maximize this, okay, or parameters, whatever parameters may come. And in particular, remember X is a random variable. So, and we saw it's a decoder parameter theta, which is relating to that random variable X given Z, right? So now log P theta is just the same, except that I've tacked on an additional expectation. Okay, this expectation is with respect to Z, but you can see that there is no Z in this underlying term inside the bracket. So I can always add an expectation like that. So for example, let's say X is a random variable which takes value 0s and 1s, and Z is a random. Okay, let me not use X. Okay, let's say W1 is a random variable which takes 2 values. Okay, and W2 is a random variable takes 2 values. Okay, if I'm taking, I'm looking at probability of W2. Okay, if I take expectation with respect to W1, there is no impact, right? That's because the term inside has nothing to do with W1. Okay, so the first operation is just adding an expectation. Why is that? Because ultimately I want to somehow figure out how to maximize this likelihood, and to do that I'll somehow reduce after several steps to somehow a reconstruction loss, the loss function we were seeing for autoencoder, reconstruct plus a KL divergence term. So that's my objective here. And so that's why first step is a manipulation. I just added an extra arbitrary expectation here. And then I look at the term inside, P of X is actually equal to P of X times P of, it's just P of X given Z times P of Z divided by P of Z given X. Okay. So this is just Bayes rule, or in general, if I have a marginal distribution like this, I can, this is just, if you bring it over here, this is, so this is actually equal to P of X comma Z. Okay, so this is just a manipulation of P of theta, so P of X into a term involving three, a numerator and denominator, 2 terms in the numerator and 1 term in the denominator. Why are we doing this manipulation? As I said, it's all about getting to an appropriate, like this should be equal, or maybe less than equal to, and so on. we want to maximize this. Okay, that's the maximizing likelihood, and we'll see that that will be equal to maximizing or let me just do somehow like minimizing this term on the right hand side, or let me say negative reconstruction loss. Then it's the same as maximizing. Okay. I mean, we'll get there, but that's the general idea of what I'm trying to do here. Okay, once I got these three terms using Bayes' rule, then I multiply and divide by the same term now. Okay, so if we multiply and divide by the same thing, it's a constant. But there is a reason why we are doing this. So these are tricks. This is one trick. This is trick number two. So this is a distribution over Z given X. Okay, so previously, so recall this was a distribution over Z given X. We have the same distribution here. Okay, we're going to multiply and divide. So there's nothing to explain over there. Now, because of that, now we can split our expectation into terms. Okay, the first term is going to be just this p of x given z. Okay, so and I'm isolating this because this is essentially going to give us the reconstruction error. The second term is going to involve this guy in the numerator, and I'm sorry, this guy in the denominator and this guy in the numerator. And I put a minus sign so I can flip the numerator and denominator because there's a log here. Okay, that's the second term. And the third term is what's remaining. This guy tick marked and this guy tick marked. Okay, those are the three terms. This is just again a manipulation. You just log of a times b is log of a plus log of b. So we can split it this way. Okay. So we did that. Now, I mean, we split it because we wanted to get into forms which look like the KL divergence I just defined. So you can see that expectation over something of log of the same thing divided by another distribution is the KL divergence between two distributions. Okay, the numerator distribution and the denominator distribution. Similarly, same thing here. Z is expectation with respect to a distribution this distribution, and that's in the numerator as well as a different distribution in the denominator. So it's a KL divergence between these two. Okay, so it's just a manipulation of this log likelihood of the data into three terms. Okay, now let's focus on these three terms. What we're going to do is say that we use one key property of KL divergence, which is that the KL for any pair of distributions is always greater than 0 or greater than or equal to 0. Okay? So what we'll do is one trick, which is to drop the third term. Okay, if we drop the third term, this is going to be a less than or equal to. Okay, if till now there's equality, it will become less than or equal to if I drop the third term. Third term is positive. So if I drop a positive term, the right hand side is going to be smaller than the left hand side. Okay. Now, if we focus on the first two terms, this term, you recall if p of x given z, if you go back to the decoder, it's actually p theta of x given z is actually producing a normal distribution, right, with some mean and some covariance. Log of the normal distribution is a squared loss, basically, squared loss. Right? I mean, log of e to the power minus something like normal distribution is going to give you a squared term. Okay, and in particular, we are asking the probability of xi. Okay, so where is it? Did I miss? Okay, so this term is going to give us essentially a term which looks like x I minus x hat I, the whole square. Okay, this is a squared loss. So you can think of x. Sorry, let me just use mu of what is the representation I used? Yeah, going from z to x, I used mu of x given z. Okay, so going to be mu of x given z. Okay, given z, this is exactly the mean, and your loss function actually it should not be like this. It should be also sigma of x given z inverse. Okay, so your loss function will be something like this. Okay, and this looks like a reconstruction loss. Okay, if sigma's identity is just the pixel wise difference between what you predicted, the mean prediction versus what's the ground truth. Okay, and the second term, this is the second term, this is the first term. The second term, if you zoom into it, this term here is the KL divergence between what we care about. We want the p theta of z to be Gaussian. Okay, we know it's Gaussian. I mean, we want it to be Gaussian. That's our desired thing. And we want to ensure the encoder's parameters phi are such that that this distance, the scale divergence between the encoder's parameters, this conditional probability, and the distribution that we care about, the Gaussian, is minimized. Okay, that's the KL divergence term. So those are the two losses. Okay, it's just a and this whole thing, the two losses, these two losses that I said, let's forget about the third term. This is called evidence lower bound. Okay, and so the word variational comes into this whole modeling. Variational autoencoder comes in because we want to learn the parameters to maximize likelihood of the data, the marginal likelihood of the data. And for that, we are going to maximize a lower bound. Okay, so we are actually going to do a optimization step. And because we're doing an optimization step, we use the word variational. Variational just means, you know, variational just means it's related to an optimization, explicit optimization step. Okay, I mean, so we're not gonna. This is informal, but that's what it essentially means. The variational word is just because we are going to maximize a specific optimization objective. In this case, the objective is called evidence lower bound. And by the way, this is all principled because it comes from us focusing on maximizing the log likelihood. Okay. So let's go back to VAE. Although those were the densest slides, but let's coming back to the VAE. This is how it looks, right? We have the input data. We produce mean and covariance from which we sample Z. Again, we produce a mean and covariance and produce a sample X hat. Okay, so which means, so think of it this way, right? So encoder, we have an image of a, let's say, person. So it's fed through a CNN. Okay, but the CNN is essentially a CNN block which is producing a mean and covariance from which you're going to do a sampling. And again, you're doing a decon, the transpose con block. It's producing a mean image and a covariance of the image from which we are sampling an image. Okay, that's what's happening here. And then so that's what's happening in terms of the whole training example. Whole training process to learn the parameters. But once you have the parameters, you just focus on the decoder only. So you go from Z all the way to X hat. And so the way you do it is sample Z from the normal 0, 1, 0, identity matrix. That's what we assumed we preferred. From the Gaussian distribution, we pass it through our decoder network, the decon network. We get the mean and the covariance, and we can draw from the normal distribution. Okay. And here is an example of doing that for, I think, both CIFAR 10. So the three data sets, CIFAR 10, which is what you guys have worked on. I think the last one is the data set, is the phases data set. The first one is the MNIST data set. Okay. So here you can see what they did is chose the dimension of Z to be 2 dimensions. Okay, Z is 2 dimensions, and we know that Z has to be normal distribution. So they are trying to see, okay, how does the output vary, the mean image vary as I change the first coordinate and the second coordinate. You can see I'm going from 7 to 9s to 6s, right? 6s, 9s here, 3 here, 1s here, and so on. Okay, so this is just the uh, mapping from the latent variable to the output image. And by the way, these are images that are generated. Okay, so once you have learned from the data set of MNIST images, we forget about the MNIST images. So all these images are supposed to be new images. Okay, everything that is captured in the decoder network. Similarly, CIFAR 10, these images are supposed to be new images. Sorry, that's not good. These things are supposed to be new images from the decoder by passing an appropriate Z. And similarly, the last one is also the same. Okay, new faces. Any questions about this part? There was some. Um, so what I did is explain autoencoders. Then I uh, explain autoencoders, and then I said there's need for probabilistic model here because we need to generate new samples. And so what we did is augment an autoencoder with a predicting means and variances, right? And then we looked at the architecture of the variational autoencoder. We saw where exactly the mean and variance are getting predicted, both at the encoder level as well as the decoder level. And then we figured out, okay, we have endured the architecture with this mean and variance prediction part. Uh, but how do we train it? How do we train the parameters of the encoder and decoder? We did it in a principled way. We started from the maximizing the log likelihood of the data, and we somehow broke it into three terms, and one term we dropped, and two of the terms, one was related to uh, the decoder reconstruction error, the other one was related to encoder and the our preference that the distribution over the z space is actually Gaussian. Okay, so and then we can just solve it using any, you can just maximize for the parameters for that objective. Okay, minimize the objective given the parameters, and you can do that using gradient descent and so on. So that's VAE. Um, you can see that the images are somewhat blurry, and you'll see today we don't have time, but next time I'm going to continue with GANs, and we'll see that GANs will produce much more sharper images. Okay, um, so so that's the I guess idea behind VAs. It's a model that's somewhat recent. I think 2014, uh, only 6 years. So it's a very interesting way to capture the distribution of unstructured data, in this case distribution of the true underlying images in some sense. Are there any questions in general?
Why do we restrict Z to be from Gaussian distribution?
That's the architecture for this vanilla VAE that we chose, and it doesn't have to be Gaussian. So the P of Z, we just chose it to be some known distribution that we prefer. Okay, if you don't express preference, then the problem is not well defined. So you have to say something about what is the distribution that you prefer. Otherwise, training the encoder is going to be difficult. Encoder's parameters.
But it could be some other distribution too, right?
Yeah,
If
yeah. You can choose anything else. If
okay,
you choose something else, then yeah, appropriately the definition of I think appropriately this will look different. Okay, the KL divergence expression will look different in the loss function. That's all.
okay,
For Gaussian, it's easy because remember there's a log of probability. So if you have a Gaussian, log of probability just becomes some sort of a squared loss type of expression. Okay,
okay.
because Gaussian has e to the power minus squared function, right?
Yeah, yeah.
That's all. Yeah, you can change this so you don't have Gaussian, single Gaussian. You can have mixtures of Gaussians if you want, or you don't have to be even Gaussians. You can have other distributions like Dirichlet if you want. You can change them. It's up to you. It's up to you. But the standard vanilla VAE is described in this way. Any other questions? Okay, I realize the date on the this iPad is wrong. Okay, but anyway, so I think we're gonna cover GANs in the next lecture. So model of that. Next week, as I said, we're gonna look at project related activities, and I'm gonna send an email, send information about that on Slack. Okay, so if there are no questions, thank you so much for attending.